This video is an introduction to the photoelectric effect. In addition to the reading from Hyperphysics and OpenStax, you should read over page 3 and 4 from the Spiral Physics textbook. On the top of page 3, it explains that the suggestion that light acts as a particle rather than a wave can be dated to Planck's explanation of black-body radiation. We are not going to look at that in class, but when you do the reading from OpenStax, before the photoelectric effect section, there is a section on black-body radiation. So that is not assigned reading, but if you want to read more about that, you can do so in the OpenStax physics textbook. We are going to look at the photoelectric effect experiment because it gives a simple and convincing explanation of light being particles, or having to think of light as particles rather than a wave. In the photoelectric effect experiment, we have a beam of light which is directed onto a metal plate, and it has been noted that the energy that is deposited by the light on the plate is sufficient under certain conditions to free electrons from the plate. The energy of the freed electrons is measured, and these early experiments revealed 3 surprises which are listed here. Those surprises are that when the intensity of the light was greater, this did not result in the electrons having a greater energy. And below a threshold frequency, no electrons were emitted. And the electrons were emitted almost right away, so within a nanosecond. Whereas if you're thinking of light as a wave, you would expect that there would be a time lag when the energy would collect before the electrons were emitted. If you're thinking of light as a wave, you would expect that with more intensity, the electrons would have greater energy, and that when you reduce the frequency, you would still have electrons emitted, but just with a smaller energy. So Einstein realized that these surprises were not really surprising if you considered light to be a stream of particles. And the energy of each particle, called a photon, is Planck's constant, which is 6.26 times 10 to the negative 34th joules times seconds, times the frequency of the light. With this in mind, and you can read this on the bottom of page 3 and the top of page 4, we can explain these 3 surprises. First of all, electrons were emitted almost instantly because the energy comes in bundles. That would be the photon. And when one photon hits an electron, the energy is given to the electron right away, and you don't have to wait for it to collect. When a photon hits an electron, and the energy of the photon is not enough to release the electron, since you have each photon with the same amount of energy, no single photon has enough energy to release the electrons below a certain threshold frequency. And the greater light intensity does not result in the electrons having greater energy because each photon gives energy to one electron. The more intense light has more photons, but each photon still has the same energy. So you can read more about that in your Spiral Physics book and on the Hyperphysics website and in the OpenStax physics textbook. The energy that a photon has goes into releasing the electron. The energy needed to do that is the work function that we have here. And the rest of the energy is the kinetic energy of the electron. We can rewrite this equation and say the energy that the electron has is equal to the energy of the photon minus the work function, which is the energy necessary to release the electron. And the energy of the photon is the frequency times Planck's constant, so we can put that in here. Now we're going to take a look at problem 20. In problem 20, you have a graph given to you, just similar to the graph that I've drawn here. We have the kinetic energy on the y-axis and the frequency on the x-axis. This is similar to what you are plotting in the photoelectric effect experiment. In part A, for problem 20, they ask if the intensity of the light striking the sodium metal was doubled and experiment reperformed, sketch and label the line that would represent the results of the experiment. So on page 20, you should only have one line right now, which is for the maximum kinetic energy of photoelectrons emitted from the sodium metal as a function of the frequency. If you increase the intensity, nothing in this equation changes here. So increasing the intensity increases the number of freed electrons, but it does not change the kinetic energy that they have. So the line for part A would be the same as the initial line that we had. In part B for problem 20, if the metal had half the work function of sodium and the experiment was reperformed, we are to sketch and label the line that would represent the results of this experiment. Well, if you look at this equation here, it has the form y is equal to mx plus b. So the slope of the line is the frequency, or the slope of the line is Planck's constant. On the x-axis, we have the frequency, and the intercept is the negative value of the work function. If the work function was half as much, then our intercept would be here. And if you're using the same frequency light, the slope would be the same. So the line that we would have in this case for part B would have the same slope, but a different intercept. So this is the line that we would have in part B. In part C, we're asked what feature of the graph represents the work function. Well, we just said the intercept is the negative value of the work function. So for part C, that would be the absolute value of the y-intercept, or you can say what feature of the graph represents the work function. That would be the negative value of the y-intercept. And for part D, we want to know what feature represents Planck's constant. That would be the slope. Okay, and that concludes our introduction and also problem 20 from the photon.